magnetic dipole moment of a revolving electron. And we know in an atom, electrons revolve around the nucleus. We know that in circular orbits or elliptical orbit or whatever. Now, in our discussion, we can assume that electrons revolve around the nucleus in circular orbits. Now we know that movement of charge, flow of charge is called current. Now let us say that a electron of charge E is moving or revolving in a circular orbit of radius r around the nucleus in anticlockwise direction. Let us say here is the nucleus with Zd amount of positive charge and a electron of charge E is revolving around this nucleus in a circular orbit of radius r with uniform speed v, or you can say uniform angular speed omega, whatever, in both cases you can derive the expression v in anti-clockwise direction, right? Now electron is revolving anti-clockwise direction, that means you can say charge is flowing in the clockwise direction. Electron is flowing in anti-clockwise direction, therefore you can say current is flowing in the clockwise direction. I may change this color. This is the current direction and this is the direction of the electron. Electron moving in anti-clockwise direction, we have assumed. Then it is equivalent to flow of current in the orbit in clockwise direction. Thus, the orbit of electron is considered as a tiny current loop. Right? This loop, this orbit of the electron can be assumed or can be considered as a tiny current loop. Current is flowing in this direction. Is it clear? Now let us say the mass of the electron is m and uniform speed is v. Therefore, we know that there is an angular momentum of the electron, and the angular momentum of the electron is I. L is equal to what? What is L? L is R cross P. R cross P. P is mv. And see here, this is direction of R, this is direction of V, and R cross V, R cross P. We can say this is R. This is R, direction of R, and this is V. V means P. Therefore, R cross P. What is the direction of R cross P? It is normal to the plane of the orbit, but in the upward direction or out of the board. This is the direction of P. No, this is the direction of L, angular momentum. And these two are perpendicular. Therefore, magnitude of L is RMV, or you can say MVR. If we write this in the form of omega, then we can write MR into V is what? R omega. You know that. Therefore, MR square omega. This is the angular momentum of the electron. Right? And orbital motion of electron, consider the current I. Consider the current I in the clockwise direction. And that I, the current I. What do you mean by current? Current is what? Flow of charge in unit time. Flow of charge in unit time. If the electron, the time period of electron, complete one revolution is capital T, then I equals to E by T. Then you can say after time T, E charge flows through this cross section. Now we know that the amount of charge flowing through any cross section in unit time is called current. Therefore, in T time, E charge is flowing. Therefore, current I is equal to E by T. Charge flowing through unit time is charge by time. That means E by T. Now, what is T? T will be T is the time required to complete one revolution. Now, to complete one revolution, the total path is 2 pi r and speed is v. Therefore, we can write EV by 2 pi r. This is the current. Now, we can assume this as a current loop. Which current I is this? Therefore, this current loop behaves like a magnetic dipole. With dipole moment M is equal to I into capital A. This is the dipole moment, and I is equal to EV by 2 pi r and A is pi r square, area of the loop. And from here you can write EV r by 2, or you may write this as ER by 2 into r omega. V is r omega, and from here you can write E omega r square by 2 also. This is the magnetic dipole moment of an electron. And what is the direction of this magnetic dipole moment? See here, from this side current is clockwise. Therefore, in this side there will be a south pole. But from that side, from opposite side of the board, the current is anti-clockwise. Therefore, in that side there will be a north pole. Therefore, magnetic moment direction is from south pole to north pole. That is, it is also perpendicular to the plane of the orbit, and it is inward, that is into the hole. Or we can say L and M are in opposite directions. The direction of magnetic moment is in the inward direction, that is in a direction opposite to the what? Opposite to the angular momentum. Now L is this and M is this. Just write M by L. M is magnetic dipole moment and L is angular momentum. Now M is EVR by 2, right? EVR by 2, and L is MVR. L is MVR, and from here you get E by 2, right? Or in vector form we can write M is equal to E by 2M into L, right? M is equal to E by 2M into L, and in vector form we can write M is equal to minus E by M into 2L. We put here one negative sign because this indicates that M, that is magnetic dipole moment, is in opposite direction of the angular momentum. And this ratio M by L, that is the ratio of magnetic dipole moment and angular momentum, is called the gyromagnetic ratio. Gyromagnetic ratio. This is called gyromagnetic ratio, and this is constant. See here, E is electronic charge, M is electronic mass, and these two are constant. And you get it for electron. You may put E is equal to 1.6 into 10 to the minus 19 coulomb, and M is 9.1 into 10 to the minus 31 kg, and you will get the ratio as 8.8 into 10 to the power 10 coulomb per kg. This is called gyromagnetic ratio, and gyromagnetic ratio for electron is 8.8 into 10 to the power 10 coulomb per kg. According to Bohr quantization quantization law, angular momentum of an electron is integral multiple of h by 2 pi, right? According to Bohr's postulate or Bohr's quantization law, we know that angular momentum m is m into h by 2 pi, where m is an integer 1, 2, 3, etc. H is called the Planck constant. Do you know that? We know that. Now if we put this in this term, then what will we get? According to Bohr's quantization law, L is mh by 2 pi, where h is Planck constant and m is an integer. And from here we can write meh by 4 pi m. n into eh by 4 pi m. Now the lowest value of n is 1. Therefore, the least value of magnetic dipole moment, capital M, is Eh by 4 pi m. Now all these are constants. E is constant, H is constant, M is constant, pi is constant. Right? And this Eh by 4 pi m is termed as mu b. Is termed as mu b and is called the Bohr Magneton, denoted by mu b. This is Eh by 4 pi m is called Bohr Magneton, and it serves as natural unit of magnetic moment. Mu b can be taken as the unit of magnetic moment actually in the nuclear and atomic physics. Right? Bohr Magneton can be defined. Now, what is the definition of Bohr Magneton? Bohr Magneton can be defined as the orbital magnetic moment of an electron circulating in the innermost orbit of the atom. N is 1, that means innermost orbit of the atom. Bohr Magneton can be defined as the orbital magnetic moment of an electron circulating in the innermost orbit of the atom. And we can put H, E, N, and what will you get? Mu b, you get 9.27 into 10 to the minus 24 ampere meter square. You get 9.27 into 10 to the power minus 24 ampere meter square. You put here E is equal to 1.6 into 10 to the minus 19 coulomb. H is 6.62 into 10 to the power minus 34 joule second. Pi and M is 9.1 into 10 to the minus 31. You will get 9.27 into 10 to the minus 24 ampere meter square. This amount of magnetic moment can be taken as a unit of magnetic moment called the Bohr Magneton. Besides the orbital moment, the electron has an intrinsic magnetic momentum also, which has some numerical value also. Besides the orbital moment, this is the orbital magnetic moment, right? The electron has an intrinsic magnetic moment, which has the same numerical value of Bohr Magneton. It is called the spin magnetic moment. It is called the spin magnetic moment.